The last type of example I'm going to include for you guys is a complex circuit. A complex circuit is very simply a circuit that has both series and parallel arrangement combined in one circuit. This takes a little bit more thought when trying to analyze this. However, we start the same way we've started all our previous examples. We should name each resistor. So if I call this R1, R2, R3, and R4, that will allow me to keep my data nice and organized. So my first resistance is 2, my second resistance is 4, my third resistance is 3, and my fourth resistance is 5 ohms. Now the total becomes a little bit more difficult. Before we do that, we should also note that the total voltage for the entire circuit is 9 volts. So what we need to take a look at here is, well, R1 is 2, that's fine. Since R2 and R3 are in parallel, we need to find a way to combine those. Hopefully you remember that if we want the equivalent resistance in parallel, we add up the reciprocals. In this case, 1 over 4 plus 1 over 3. And if I raise that to the negative 1, I get my equivalent resistance, which will be 1/4 plus 1/3. Raise that to the negative 1. 1.71 ohms. So 1.71 ohms is my equivalent resistance. As you can see, I'm rounding this. That rounding will probably affect my results a little bit, but nothing drastic. So we know that, and here's a good way some people do this that I find this may help. If I'm combining these two, well, my equivalent resistance for these two is 1.71 ohms. So now if we take a look, I have a 2 ohm resistor. I have an equivalent resistance, which is 1.71, which is really just replacing these two with 1. So this equivalent 1.71 is now in series with these two. So I have 2 plus 1.71 plus 5, which is going to give me my total resistance. So 5 plus 1.71 plus 2. And the reason I add these is when I combine them, you pretty much replace them with one hypothetical resistor, and you then have 3 in series. So 2 plus 5 is 7, plus 1.71 will give me 8.71. So 8.71 ohms is my total resistance. If we take a look, I have my voltage, I have my resistance. Again, hopefully we're starting to see that Ohm's law will allow us to determine what the current, the total current in this circuit is. All right, so if we rearrange, the total current is my voltage divided by my resistance. So if I take 9 divided by 8.71, I should get my total current for this circuit. So 9 divided by 8.71 gives me 1.03, I will round that to. So my current, my total current, is going to be 1.03 amps. Now here's where things become a little bit tricky. I will separate these just so we don't have too many numbers and too much confusion. If I separate these, the best way I've found to work with this, well, there's two ways we can deal with it. Immediately, we should pick up on the fact that if I have 1.03 amps of current, that means I have 1.03 as I travel through here. You should immediately see that I have no other options yet, so when I pass through R1, I must still have 1.03 amps. My amps, my current will only decrease or change at all when I hit a junction where that current has to split between two or more paths. So I have 1.03 amps of current, 1.03 amps of current, 1.03 amps of current. Well, I passed through resistor 1 with 1.03 amps. So what that tells me is resistor 1 must have 1.03 amps of current. Now that 1.03, that splits when we get to this junction. So we don't know exactly what the current is in here or exactly what the current is, but we know that when we add them together, they must equal 1.03. So another way to look at this is to say when I add whatever these two currents actually are, they're going to have to actually add up to 1.03. I don't know what the actual currents are, but I know that combined they have to equal 1.03. I had 1.03 going in. When they come back together, I must have 1.03 going out. If we follow along with that, you can also see that, well, if I have 1.03 going out, I must also have 1.03 pass through resistor 4, which tells me my current is 1.03. which would then tell you that the current here is 1.03, and the current all the way back to the other terminal of the voltage source would also be 1.03. We have two ways we can look at this now. Well, let's start easy. I have the resistance and I have the current of resistor 1, and Ohm's law tells me current times resistance will give me voltage. So if I multiply 2 times 1.03, I should get my voltage is 2.06 volts. That's essentially, again, you can think of it as that's what it cost me in voltage to get through resistor 1. And what does it cost me to get through resistor 5? Well, 5 times 1.03 should give me 5.15 volts. So there's two ways we can look at this. Well, we know that if we're passing through here, we have to spend a certain amount of voltage. Well, if I have 9 volts to spend, and I have to spend 5.15 going through resistor 4, and I have to spend 2.06 going through resistor 1, well, I should be able to figure out how much I have left to get through here if my total voltage is going to have to add up to 9. So if I kind of come on the side over here, and I take my total, which is 9 volts, I'm going to subtract the voltage that I have to keep on the side for resistor 4. I need that much left over once I pass through everything else in order to get through resistor 5. I need to have 2.06 to get through resistor 1. So if I take 2.06 away, this should give me the total voltage that I have left over to get through this section. So if we pull in the calculator again, well, 9 volts is what I'm starting with. 5.15, I have to make sure I have that in order to get through this resistor over here, which is resistor 4. I need to have 5.15 volts. I'm going to subtract from that the 2.06 volts that it's going to cost me, so to say, to get through resistor 1. So if I subtract 2.06, what I'm left over with is 1.79 volts. So 1.79 volts is what I have left over to spend, again, so to say, you're not really spending, electrons aren't spending money or anything, but you have this many volts left over to spend through this section. Now the important concept becomes, well, if a charge travels through here, well, when it hits this junction, it can only go through one of these two paths. So if I go through this path and then continue on, well, I've only passed through one resistor in here, and I had 1.79 volts to spend, so I must spend 1.79 volts through resistor 2. So my voltage must be 1.79 in resistor 2. Well, what if a charge didn't take the path through resistor 2 and took the path through resistor 3 instead? Well, the charge would spend, so to say, 2.06 volts going through resistor 1. Well, it has to spend some kind of voltage in here, and it spends 5.15. Well, it only passed through one resistor in here, and it had 1.79 volts to spend through this section. And since if you take this path, you only pass through one resistor, well, you must spend all that voltage in that one resistor. So my voltage in resistor 3 must also be 1.79 volts. So if we take a look, let's double check. I have 9 volts to spend. I spent 2.06 traveling through resistor 1. If I take this route, I spend 1.79 passing through resistor 2, continue through resistor 4, which costs 5.15 volts. And when I get to the end, well, if I add up resistor 1, resistor 2, and resistor 4, that gives me 9 volts. Well, what happens if I had a charge that passed through resistor 3 instead? Well, I have 9 volts to spend. I have to spend 2.06 because I have to go through resistor 1. I have to spend some kind of voltage through resistor 3, and I need to make sure that I have 5.15 left over. Well, 2.06, which is resistor 1, if I add to that the voltage spent in resistor 3, 1.79, and then I add the voltage 5.15 that it cost me to get through resistor 4, that will also add up to 9. So my voltage makes sense. Some of you may have noticed that if I had just taken my equivalent resistance and my equivalent current and multiplied them by one another, I would have also wound up with 1.79 or very close to that. So that is another way you can go about it if you don't want to go through well, I'm going on a trip and I need to spend voltage at each location. You can also take your equivalent resistance, multiply it by your current, and you will also get 1.79. Hopefully you now see that I have a resistance and I have a voltage for both resistor 2 and resistor 3, so I should be able to find my individual current in each of these. So if I pull my calculator back in, let's look at resistor 2. I have 1.79, the resistance is 4. Ohm's law tells me I should divide these numbers to find current. So we have 1.79, which is my voltage in resistor 2. I'm going to divide that by 4, which is my resistance, and I get 0.4. I'll round that to 0.45. So my current in resistor 2 will be 0.45. I have 1.79 volts for resistor 3. So 1.79 volts for resistor 3. And if I divide that by my resistance, as per Ohm's law, I will get 0.59. I'm going to go ahead and round that to 0.60. So 0.60. If we double check now, we already went through, my voltages will add up. No matter what path I go through, I will have 9 volts of total potential spent. If we take a look here, these two numbers have to add up to 1.03. If you add these up in your head now, clearly you'll see they add up to 1.05, a little bit more than what we want. However, as I explained before, we did a lot of rounding here. Okay, this was not actually 0.6, it was 0.59666 repeating. This was not actually 0.45. We did a little bit of rounding. I also rounded these numbers as well. As long as you're getting in the ballpark, everything should line up. So hopefully you start to see we can check through the voltage. We can check to make sure the currents line up. And complex circuits, that's the basics of it. A little bit more complicated. If you break it down and you think to yourself, I have 9 volts to spend. I have to spend all 9 volts no matter what path I go through. I have found that that tends to be the easiest way to analyze these without getting confused. Hopefully this helps.